Oh, good evening, guys. How are you?
We're good, especially the part that everybody just missed.
Yeah. Fortunately, my finger was a little bit slow on the button. It's a good thing for all of us. All right. I'm Rich Ozer. I'm here with Gerald McKeegan and John Curry, and welcome to
Hi, everybody.
Chabot's virtual telescope viewing. And
Hi there.
yes, it is a clear night, and the humidity is low. It's a little bit windy. The seeing is a little bit shaky, but I think we'll be able to use the telescope tonight as we've averted all the major crises. Um, Before we get started, I want to remind everyone that the Chabot Space and Science Center is still closed, although we are planning on opening in November. We've got all kinds of exciting things coming up, including a new partnership with NASA, and there'll be new exhibits and new activities as a result of that. But you have to wait till November for all of that to start. In the meantime, we are counting on our memberships and our community to help us with donations. I want to thank Fremont Bank in particular for sponsoring this program and others. And we appreciate everybody's involvement. So thank you for being here, and thank you for your assistance over the last many months, dragging on many months, but we do appreciate it. Um, so, guys, before we get started with the telescope viewing, I did have the opportunity to process some of the images from last week. I'm time
How'd
traveling.
you do that?
Yeah, we want to
Yeah,
see
how did I
this.
do that? Last week, and I wanted to show everybody the results of that because we were starting to speak theoretically about what people should see rather than what they were actually seeing. So whenever that happens, it's a good idea to process the photographs. So the first thing I want to show you is M13, and I'm going to share my screen here. And we were looking at M13 last week, and this is what it looks like when you stack about 9 or 10 of the M13 photos that we took. These were 20-second shots. I believe they were 20 seconds. They were either 10 or 20 seconds. And what you can see here, and what my objective was in the processing, was this propeller shape that you can see right here. There's one leg of it, there's another leg of it, and there's the third leg of it. Now, M13 doesn't actually have a propeller, although that would be pretty neat. What it has
How do you
are,
think it gets
yeah,
around in the sky?
that's how it moves. Yeah, wherever there's a propeller, there's propulsion. Now these are dust lanes that are obscuring the bright stars behind M13. Uh, excuse me, behind the dust lanes, and M13, if it didn't have those dust lanes in front of it, would be a much brighter ball, and you wouldn't have that obstruction. Uh, but
It's
we should
pretty
probably
bright
talk about
already.
what, yeah, it's pretty bright
Yeah.
already. So M13 is what's called a globular cluster, and it is consisting of hundreds of thousands of stars, and they're all gravitationally bound to one another. They were probably all formed together out of the same giant molecular cloud of hydrogen, and they're very ancient stars. They're in the neighborhood of 13 billion years old, and we know they're the old stars because we're able to look at their spectra, and we're able to look at the characteristics of the individual stars in the cluster. And we know that they're old because they don't have any of the newer materials that evolved as the universe aged. So they consist mostly of hydrogen, and we don't see the heavier elements. So we're able to deduce that they're some of the oldest stars in the known universe in these globular clusters. So anyway, that's M13, and we're going to look at some more globular clusters tonight. But before we do that, I want to show you the second object that we photographed, and that is M27, the Dumbbell Nebula. And that we found rather hard to see. You guys able to see that? Or do
Not
I have to
yet.
share it
Not
again?
not
Okay,
yet. You have to
let me
reshare it.
let me reshare it. Share screen. Zooming around here. Okay, there we go. So what I wanted to do is bring out the shape that the Dumbbell Nebula is known for. There's a lot of other details in the Dumbbell Nebula that this photograph does not show because we really didn't have enough data. This is a series of 5 images. Each one was 60 seconds long. So we really didn't have a lot of data to work with, but I did want to bring out the shape of this hourglass here, which is why it's called the Dumbbell Nebula. It looks like a hand weight, a dumbbell that you would lift. Hence its name. You could see a little bit of the ring around it here. It's barely visible, and a little bit of red over here, which is indicating hydrogen, and the blue is indicating oxygen. Even though hydrogen is the most abundant element in this nebula, the oxygen glows very, very brightly and tends to overwhelm any of the other elements that are glowing. But anyway, that's the Dumbbell Nebula, and that's what I wanted to show you. And we'll probably do something similar with whatever objects we're looking at tonight. So, guys want to start with M22?
Yeah, we are on it.
We're on it already.
Yeah. So we're using our 36-inch reflecting telescope.
It's going to take me
the one we call Nellie. And we have pointed it at M22, which is another globular star cluster, I believe. And Richard's got a camera on the telescope, and he's going to connect that camera up so that you can all see what his camera is seeing.
It's going to take me a sec to get there. John, you might want to talk about what we were reading about M22 a minute ago.
Let me bring that back up. M22 is considered one of the finest globular clusters in the sky. Now, why is that? Oops, I'm on the wrong thing here.
Here we go. All right, can you guys see it? Yeah. I'm gonna go for a longer exposure.
So for globular clusters, this is one of the brightest ones in the sky. It's in Sagittarius. And if you know Sagittarius, it's near the top of the teapot. And it's close to or it's in the direction of the central bulge of the Milky Way galaxy.
There we go. That's a little bit brightened up.
That's good.
Yeah. And as I suspected, it fills the view that we get in Nellie. Nellie has got an amazingly narrow field of view because of the magnification that we get out of this telescope. And this globular cluster extends beyond the field of view that the telescope provides us. This was discovered in the 1600s?
1665, yeah.
1665. So it ended up in Charles Messier's catalog as a result, but it's probably the earliest globular cluster that was ever recorded by an astronomer. And it's been studied extensively in recent times. And one of the reasons for that is that it sits in front of the bulge in the Milky Way galaxy. So it's really, because it is gravitationally so massive, and the stars are gravitationally massive as well, many of them, they're able to do what's called microlensing with this globular cluster and use it to view stars that are behind the cluster, and in order to study the central bulge of the Milky Way. I never knew that until tonight. It's actually an interesting topic that I'm going to learn more about, but it's called a microlensing observing technique, and this is one of the few objects that you can do that with.
Lensing, right?
It's like gravitational lensing, but it's using star clusters rather than galaxies, and it's much more nearby, right? So speaking of nearby, this is one of the closest globular clusters to Earth. It's only 10,600 light years away, only
Only, yeah.
a mere jaunt in the overall distance of things. But that's
one of
probably
the closer ones. So
yeah, it is definitely one of the closer ones. Like M13 and the others are anywhere from 30 to 60,000 light years away, and so this is right in our neighborhood.
It's also a distinctly elliptical globular cluster. So as opposed to just a sphere, it's more elliptical.
So one of the other things that was mentioned is it's one of the two globular clusters that has a visible planetary nebula in it. I don't know where that is in here, and I'm guessing that we can't see it.
We went
without a much longer exposure.
We went looking for it earlier, but we couldn't find it.
Yeah. I was teasing apart all those individual stars in there, looking for the nebula. All right.
So this is one of about 150 that orbit around our galaxy.
Yeah, 150 globular clusters.
Right.
Yeah, its diameter of 32 minutes is slightly larger than the full moon too. So that's something to make note of.
Tim pointed out that M22 and M13, which, M13 we looked at the photograph a little bit earlier, and M22 is what we're looking at right now. They're both excellent binocular objects. So if you live in the city, this is one of the objects that, if you know where to look, will be very visible through a pair of binoculars, even in the city. Obviously, if you're in a dark sky location, then you would certainly see it along with many, many other objects. But this is a good city object.
Yeah. Sky Safari actually says that it's naked eye visible in a really good dark sky location.
Yeah, I was just going to say that if you get a really dark sky location and you know right where to look, you can see it naked eye.
I've never been able to do that.
How about M13? Can you do M13?
Yes, I have seen M13 naked eye.
Okay.
Yeah. It's probably because it gets higher in the sky and I'm able to pick it out a little bit better.
For at least from our latitude, this is always pretty low in the sky.
Yeah.
So these stars are all very close together, much closer together than stars around our sun. And they're all extremely old. Globular star clusters formed at the very beginning of the formation of the galaxy. And so they're very old. The stars that we see are mostly the low mass stars that are left in the globular star cluster. When it first formed, it had high mass stars, medium mass stars, and low mass stars. But high mass stars don't last very long. Because they burn up their fuel so fast. So, this globular cluster has been around for 10, 11 billion years. And in that time, all the high mass stars have grown old and died. But the low mass stars are the ones that last billions and billions of years. And so the stars we still see shining are the low mass stars that are still left in the globular cluster.
Now, this particular globular cluster, for whatever reason, also has a higher population of red stars than some of the others. So that's one of the unusual features of this one.
Yeah. And those are mostly stars that are moderately low in mass, and they have swelled up. Mm-hmm. So the color has changed as stars swell up. The outer layers cool. The color changes, so the star may have been initially white or very pale yellow. As it cools, it goes to a deeper yellow, and then orange, and then eventually red. So anytime the color is on the red side of white, we say it's a red star, even though it may not look red.
Interesting question here. Do fast radio bursts originate from globular clusters? I have no idea.
Yeah, I'm not sure either.
Well, the fast radio bursts, the gamma ray bursts, are usually due to events occurring
There are other
at
galaxies.
galactic distances,
Yeah.
not necessarily inside the Milky Way. And so they probably involve, things like, neutron star collisions and, other cataclysmic events. And there are some globular clusters that are believed to contain black holes and might be a candidate for such an event, but usually those gamma ray bursts are coming from a much greater distance.
Well, there are interesting things going on near the center of globular clusters too, so there's always that possibility.
That's true. Yep.
Yeah, there's a lot of speculation about whether or not there's a black hole at the center. As you can see, it's pretty dense near the center.
Yep.
And at least with some globular star clusters like M15, it's so dense there. And when we try to measure the concentration of the mass, there's so much mass very close to the center that it's hard to imagine that there isn't a black hole at the center. All right. Well,
let's move on.
Next? I think we wanted to look at another globular cluster, right?
Yeah, we were thinking of jumping all the way across to Hercules and not necessarily looking at M13 tonight because we already spent a fair amount of time on that, but maybe its smaller neighbor.
Yeah, I'm going to do a little intermediate jump.
The other Hercules cluster.
Yep. All right, I am going to stop this.
Yeah, go to live view and we'll make sure.
Yeah, give me a sec here.
We'll go up to Russell Haig. Uh-huh.
Hey, not bad. That was pretty close.
We do this to get a more precise movement of the telescope.
Hey, considering the what we had to go through earlier tonight, I'm pretty happy to see that there. We were having some mechanical difficulties earlier.
Computer difficulties.
Yes,
as Gerald loves to point out.
Yes, that's true. Yes, we'll blame
Never
it on
met
the
a computer I didn't hate. Okay, here we go. So our telescope is computer controlled. So all we have to do is tell it where we want to look and it will move the telescope in that direction. The telescope aim is pretty good, but it's not perfect. So sometimes you'll see us do some intermediate moves. So we get the telescope as lined up as precisely as possible.
What Richard was alluding to before, we had some problems. The telescope and computer weren't talking to each other properly. So when we do that, we have to manually point the telescope at a known object in the sky and resynchronize it with the computer. But unfortunately, it was too early and the sky wasn't dark yet.
It's a little tough to do that before it gets dark, right? I think our focus got soft again, so I'm going to probably play with that while we're.
You want to go to a nearby star?
Yeah, would you do that, please? I want to get the focus right.
All right.
Those look blurry.
Seeing conditions are not ideal tonight, so
no, they're
not. Be having a little trouble with the focus. We try to keep it nice and sharp, but sometimes that's just not possible.
Okay, maybe you can get that in the square for me. Here, I'll give you a bullseye. It'll help.
So Richard's got his camera so that it's live. It's looking live at that star, and Gerald is moving the telescope around with a little control pad that moves it very small amounts. It makes it possible for us to zero right in on that star. And you can see that star is kind of bubbling around. That's the bad seeing conditions that we were talking about.
Then you notice the number. You see the zoomed in view up on the upper right, and you see a number underneath it. And Richard is trying to get the focus to where that number is. You go.
It's about as
below.
good as I'm going to get. Yep. And I've gone from
so
11 to 8, so that's probably
we want that number
worth it.
to be as narrow or as low as possible. There is a limit to how low it will go, but we want to get it as close to that limit as we possibly can.
All right, let's jump back.
You'll see the initials there, FWHM. It stands for full wave half max, and that's a measure of how tightly the focus is of the telescope. It has to deal with something called the point spread function. All right, let's go back to M92 again.
Yeah, I was glad you said it because I almost said M96.
No.
All right, we there?
You should be there.
All right, let's try this again.
You only got to do a 10-second exposure?
That's what I'm starting with anyway.
In the meantime, Colleen asks, good heavens, the rest of us in the U.S. are so hot, and you guys are wearing hats and jackets up there. Yeah, it does get cool up here. We're up about 1,500 feet in the hills above Oakland, California.
Well, you know what Mark Twain said.
Uh-huh.
The coldest winter I ever had was summer in San Francisco.
Yeah.
Hey, that's much better focus. All right, I like this. I'm going to actually...
On YouTube, Steve asked if we use DoorDash up here.
I saw that too.
Yeah.
I don't think they can find us up here.
Yeah. Unfortunately.
I use DoorDash down the hill.
I do too.
All right, let's take 20-second shots now. It's nice and centered, and I'll lower the ISO a little bit so it's not as grainy. This is pretty nice. Yeah, it's cool right now, but it was pretty hot during the day today.
Yep.
Yeah, I've often been up here during the daytime on a hot summer day, and these domes sit here all closed up with the sun shining on the metal roofs, and they get pretty hot and stuffy inside.
All right, so you could see how this is a notably different looking cluster, right? And the main reason it looks so different is that from the M22 is that it's much farther away, but it's the same type of thing.
It's just tighter.
And tighter, yeah.
Yeah. Yeah, this one is about 26,000, almost 27,000 light years away. So it's farther away, but it is a little bit more condensed than M22 is as well. And this one is the other Hercules cluster, M13, the image that Richard showed at the beginning there with the propeller in it, that's M13, and that's the Hercules globular star cluster that most people think about. But M92 is actually another globular cluster still in the constellation of Hercules, just in a different location. And it often gets overlooked because everybody is so zeroed in on M13.
It has its thunder stolen from it on a frequent basis. All right. Yes. So Albert, this is M92. Just saw the question come by. All right. Well, now that everybody's had a chance to see this, I think we were going to jump over to Lyra, right?
Yeah, to the ring.
Okay.
All right.
Yep.
Well, let's see.
Are you going to do an intermediate, or are we going to go
No,
straight
it's
over?
pretty close. So I
Well,
think
All right.
we have Vega almost straight up, Gerald, so you could go there if you needed. But
well, let's see what
you're not that far away from it right now. I
No,
think you could
no.
probably go straight there. Yep.
And somebody asked about the meteor shower. The meteor shower actually doesn't peak until the night of August 11th and into the morning of August 12th. So we'll be having a lot of people up here that night. We have a ticketed event, and we will be watching the meteor shower if the weather cooperates. This is called the Perseid meteor shower that happens every year in August. It's one of the better meteor showers of the year.
They tend to be bright ones.
Did you do a 30-second exposure?
I did. It's got to download. There it is. Yeah, it's not
there
bad.
There it is. All right.
Good. Good targeting.
Yeah, so this is what we call a planetary nebula. That's the general classification for these objects. This particular planetary nebula is known as the Ring Nebula, for obvious reasons. The Ring Nebula is a cloud of gas and dust that was shed by a star that has reached the end of its normal life. The star was once probably very similar to our sun, but when stars get low, I was moving the telescope.
Yeah, I see. Now it's got it. Now it's the double ring nebula.
Yeah. No, we just turned it a little bit so you can see the other lobe.
Right.
Yeah.
So
this is gravitational lensing or something.
Yeah, we could see the other side this way.
So anyway, this star reached as it approached the end of its life, it swelled up, became a red giant. Red giant stars shed their outer layers of gas. There was a lot of turbulence and internal winds being generated. And as the star swells up, its gravitational hold on its outer layers weakens. And so the outer layers of gas around the star are blown out into space over a period of 100,000 years or so, sometimes several 100,000 years. And that reduces the mass of the star. Eventually, the star can lose as much as half of its original mass. And eventually, the other thing that happens is the fusion process at the core of the star stops. So there's no longer that energy being generated at the core to try to expand the star. So there's nothing to counteract the pull of gravity, and the star kind of collapses into itself, becomes what's called a white dwarf. A white dwarf is extremely dense, very, very dense. It's what we call degenerate matter, and it's extremely hot. And it emits a lot of its radiation as ultraviolet radiation. Now, the white dwarf is surrounded by all that gas that it was expelling while it was a red giant. And that ultraviolet radiation goes out and it excites and ionizes the cloud, the atoms and molecules in the cloud. And when you do that, you get a glowing cloud. The ultraviolet radiation makes the cloud glow. And the red fringe that you see, that tells us that there's hydrogen there. And then the kind of turquoise color tells us that there's oxygen there. And then if you look carefully, we actually have a pretty good scene right at the moment here. You can see a little dot right at the center of the donut hole. And that little dot is the white dwarf.
So it's right over there.
Yep. You see a little star very faintly up and to the right of the white dwarf. That's actually a background star. So
You're looking right through
right.
the ring that way.
So
this is
Albert
cool.
asks, can we come and see a Perseid meteor? And how? I think you have to sign up for it.
Yeah.
And I don't know if we're sold out yet or not.
It's going to be a ticketed event. My understanding is they're going to start promoting it this coming week on Chabot's website. And
go to Chabot's website and click on the events page, and you should get help that way.
Hey, Bob, it's the Ring Nebula, not the cat's eye.
He knew that. He's just testing us.
He's testing us, yeah. He likes to do that.
Somebody on YouTube asked if it's possible for us to see the core of the Milky Way. We can see the central bulge of the Milky Way naked eye, in fact, if you're in a really dark location. From where we are here, naked eye, we can't see the bulge of the Milky Way because there's so much light pollution and air pollution here in the Bay Area. But if you get out away from the Bay Area, up in the mountains somewhere where you got clearer skies, you can see the central bulge of the Milky Way naked eye. Now, if you're talking about the black hole that's at the center of the Milky Way, no, we can't see it with this telescope, no matter where we had this telescope. There are a few telescopes using a very specialized technique that are able to see the exact center of the Milky Way where that black hole is. They can't see the black hole itself, but they can see where it is because there's stars orbiting around it. But we can't do that here.
So Steve asks on YouTube also, what is the size of the black hole? I mean, the white dwarf, rather. I assume we're talking about M27, and it's probably something along the size of the Earth.
Right.
It would be about that in comparison.
Yes,
that's remarkable to think of.
Yeah. As small as that object is, and we can still see it.
Yep.
Well, yeah, and you take a teaspoon of white dwarf, and it weighs about as much as a truck. So this stuff is really dense.
All right. Well, we've gotten a couple of requests here, but I'm thinking, Gerald, you worked very hard to prepare some presentations tonight to try to undo weeks of confusion. we've been asked several times over the last month or so about this phenomenon about the moon's related to the moon's wobble and orbit and the extent of the Earth's tides,
sea level,
and the relationship between those things. And we've been sharing some of the misleading headlines and stories about this phenomenon. And Gerald's been trying to figure out a way to explain it that doesn't confuse us even further. And he
Richard and I are not too sure.
Yeah,
that this
we're not
is
entirely sure
really
that's the case, but we're going to give him a shot at it. And I'm going to stop sharing my screen here.
Yeah, and you're going to need to make sure I can share screen and also that.
Yeah, I know you can share, but I need to spotlight you here.
Yeah.
So hold on for a moment. I think I hit spotlight for everyone. There you go.
There we go.
Now you all can see Gerald, not us.
Most of you, I think, are aware that there is a wobble of the moon that happens pretty regularly. It's called libration. And you know that as the moon orbits around the Earth, the same side of the moon faces the Earth all the time, but it doesn't face precisely. So if here's the moon. I don't know how well you can see that. The moon tends to do a little bit of this and a little bit of that. We call that libration. So as the moon orbits around the Earth once a month, it does a little bit of that and a little bit of that. And so when this article came out about the wobble, that was the first thing everybody thought of, is the wobble that we know as libration. But it turns out that's not the wobble that they're talking about in this article. This article was saying that the wobble of the Earth is going to cause the high tides in the near future, in the next few years, to become even higher than they have been in the past.
You mean the wobble of the moon?
A wobble of the moon? What did I say?
Earth.
Oh, well.
You see, you are confusing us.
Yeah. You guys did have
but
some
I wasn't
doubts.
sure. I didn't know if by asking that question I was making an error.
Yeah. All right. So what I wanted to do is demonstrate to you what the wobble that they were talking about is and how it affects the tides. All right. So what I've done, we're going to do a little circus act here. I brought a stick and a plate. And guess what I'm going to do? I'm going to try very hard to balance the plate on the stick and spin it. All right. So you notice that while it's spinning very fast, it's also wobbling. We call that wobble. This stuff right here we call precession. And the moon, as it orbits around the Earth, its orbit precesses the same way. So what happens is the moon goes around the Earth once every month, actually once every 29 and a half days, relative to the stars. The moon orbits around the Earth, and the plane of its orbit does this kind of a slow wobble. And it does that such that it makes one complete wobble every 18.6 years. So that affects the tides here on Earth. And I want to kind of just illustrate that and kind of show you what happens when that goes on. So I'm going to see if I can share my screen here. Get over here. Get this lovely graphic that I have here. There we go. Okay, so it's at nighttime. We're looking at the sky. Here's the horizon line down here. If you were to look straight south, let's see, there we go. You would see and draw a line from the south pole of the Earth up through the point directly overhead, the point called the zenith, and draw that line all the way down, back down to the north pole of the Earth. That line is what astronomers call the meridian. The meridian divides the sky exactly in half. And a lot of what we do in astronomy has to do with the meridian. And in fact, when you're keeping time and you talk about AM and PM, the M in AM and PM actually refers to the meridian. All right. So one of the things that we talk about is when a star or the sun or the moon crosses the meridian, it's at its highest point in the sky relative to the horizon. So the moon sometimes crosses the meridian very high and sometimes crosses the meridian very low. And the difference between the highest point and the lowest point can change over the course of time. It can be as little as about 36 degrees, but it can be as high as 57 degrees. And the difference is because of that wobble, depending on where the Earth is and the moon is in its wobble as it precesses. It can change the extent to which it can either go very high or very low. For us here in the Bay Area, when the moon is at its highest, it's almost straight overhead. And when it's at its lowest, it's quite low in the sky. So there's a huge difference, and that has to do with that process that I was describing, that 18.5-year process called precession of the nodes or precession of the orbit. All right. So that precession affects how high the highest tides are. So if we were to plot the highest tides over a long period of time, say 20 or 50 years or something like that, we would find that the maximum high tide kind of follows a cycle. It looks like this. And the crest to crest or trough to trough timeline of that cycle is 18.6 years. This is due to the precession of the nodes of the moon's orbit. So you get these 18.6-year cycles where the maximum high tide is a little bit higher part of that time, then it's a little bit lower, then it's a little bit higher, and so on. If all you were doing is measuring the change in the maximum high tide over long periods of time, this is all you would see, this cycle caused by the precession of the moon. But we have something else going on. We have global climate change and global warming. And because of that, sea level is rising gradually over time. And that gradual rise is pretty steady, and it will continue throughout this century. And of course, I'm sure you've heard all the warnings about this, and while we're talking about how, people who live close to the shoreline may be affected by global warming, by the rising sea level. They're already having problems in Florida, where there's a few communities that are close to the shoreline and they get flooded periodically during high tide. And that's because of global warming. So we have this long-term steady increase due to global warming, the melting of the Arctic ice and the ice over Greenland and so forth. And if we superimpose that on the cyclic effect of the precession of the moon, we get this. All right. So rather than it staying level, it's slowly increasing. And what that means is that when we reach a maximum like this, it's actually even more of an effect. The precession of the moon can amplify the effects of the increasing high tide due to global warming. So this article that you saw a couple of weeks ago that came out about how the wobble of the moon is going to increase the effects of global warming on the tides. This is what they were talking about. And what that means is that as we go forward in time here, we're actually going to see a dramatic upswing later on this decade in the maximum high tides because of this wobble of the moon, the precession of the moon's orbit. That's all there is to it, folks. So there's nothing sinister about it. It's a natural phenomenon that happens every 18.6 years. And because of global warming, instead of it being a nice level thing, it's actually sloping upward. Okay? Hopefully that helps.
So I've got a question, and it may be completely unrelated.
Okay.
The 18 years kept sticking in my head as being very close to the length of one Saurus.
19 point, what is it, 2 years or something like that?
Yeah, or it's 18. I think it's 18 point something, and I'm wondering if there must be some relationship there.
But what happens is there's a point when the nodes are the point where the orbit either crosses the plane of the ecliptic going north or it comes around, crosses the
Oh
planet.
yeah, so it's going to be
going
the
south.
same period. Yeah.
So those the precession that I'm talking about is actually called precession of the nodes, because the position of those nodes is changing over that 18.6 year period. So that may be related also to that. There's actually 12 different things that affect the moon, 12 different cycles that affect the moon. The monthly cycle just from the moon orbiting around the sun. There's all kinds of different cycles. I forget what all 12 of them are, but in terms of the strength, the extent to which they affect the tides, the precession of the nodes actually has the least effect, but it's a long-term effect. And that's why this article came out, is because it was something that we weren't thinking about. There's daily effects. The tides change daily. In fact, every 12 hours. And you get things like when the moon and the sun and the earth are all lined up, you get what's called spring tides. Those are the maximum type tides. And then if the moon and the earth and the sun are at 90 degrees to each other, then you get what's called neap tides, and those tides are not nearly as strong. But what this is saying is that because of this 18.6 year cycle, we're approaching a period where that cycle is going to amplify the effects of global warming on the high tides that we experience. All right.
That was excellent.
It was.
Yeah, it wasn't confusing at all.
Even with
but
the spinning
there's something I need to ask. Can you spin that plate again?
I can, except I just stepped on it.
Oh no!
Oh man!
But let me see if I can do that again. You just want to see the secret to how to do it, right?
Yeah, that's right.
So the secret is
Stephanie.
Oh, come on, Gerald. We all thought you grew up in the circus or something.
Yeah.
Stephanie wants to know how fast the moon wobbles. So can you show us with that plate?
Well, okay. So the wobble that we're talking about, the what we call precession of the nodes. I'm not sure. I'm no longer the focal point. I don't think so.
Yeah, you are.
Oh, am I?
Yep. Oh, I took you off of Spotlight. Do you want to be Spotlight? I'll Spotlight you again.
Yeah.
It's just a mouse click.
Okay. So again, it was spinning very fast, but it was also doing this. All right. And this is what we call precession of the nodes. And it takes 18.6 years for it to go all the way around and back to the start point.
So it's a very slow ride.
Right.
Yeah. You wouldn't even notice it if you were standing on the plate.
All right.
All right. Thank you. That was great.
So I either clarified things or...
No, you did. I think you did. I think we could put this topic to rest for a while.
Yeah.
But I think that we all learned something from that. Thank you.
All right.
Did you have another thing you wanted to talk about?
Well, we were thinking we might be fogged out tonight, so I also brought some stuff about the Insight. There's been a story this week about the Insight Mars probe that's on Mars, and how they've been able to better characterize the interior of the planet Mars. So
well, we could probably hold on to that story for when we might need it.
Yeah.
And I'm showing people the Ring Nebula again, which is what we were still focused on and photographing during that presentation. So I'll probably have another Ring Nebula photo next week. We
want to make sure at 10:25 here that we are ready for the big surprise object tonight.
Speaking of rings.
So do you want
Don't give it
to?
away, John.
We're really close. I was just trying to estimate how close we are, but I think
Well,
we need about another 10 minutes.
Bob Schock asked if we can point at the cat's eye, and if you want to try doing
We
that.
can give that a shot. Yeah.
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 Where is that? That's over in. That's actually pretty high up, isn't it?
Yeah, it is. May need to do a intermediate.
Yeah. I'm going to go up here and we'll stop at a star and get focused on it.
There we go.
Yeah, not too bad.
Yep.
Okay.
Now the cat's eye is another planetary nebula and kind of looks like a cat's eye. That's why it's called the cat's eye. It's not as bright as the ring, so it's not quite as spectacular on a quick instant view as we get with the ring nebula, but it's very interesting looking and worth taking the time.
Okay. Doesn't like cat's eye.
No, it's sorry.
NGC number?
NGC 6543.
Yeah.
NGC
6543.
6543.
Countdown.
Yeah.
Okay.
That makes a terrible password.
Yes, it does. Well, with the NGC in front of it,
yeah, then
it
it's a little bit better. Yeah. All right, I'm gonna go back to imaging, and I'll start the shot.
All right, we are there.
All right. Play the Jeopardy song here.
So the neat thing about planetary nebulae is that when the star blows all that gas off when it's still a red giant, it doesn't necessarily blow it all off in a nice spherical shell. It often blows the gas off in some sort of a symmetrical lobed shape. And it can be different for different planetary nebulae. It's not unusual for the gas being blown off to form an hourglass shape or a butterfly shape. It just depends. And there can be shock waves within the cloud that give it even more structure there. So Cat's Eye Nebula, which we're probably not going to see a whole lot of detail here, but it when it's photographed in high resolution, you actually see quite a bit of detail within the structure of the planetary nebula, not just the white dwarf, but you can see shock waves and patterns within it that are caused by things like planets orbiting around the star prior to it becoming a white dwarf, things like that. So you can see a little bit of the structure here.
Yeah, you can see a little bit. This is kind of elongated here, and you get kind of a whirlpool pattern here. Part of it sticks out this way, part of it sticks out this way. This is really overly processed here to give you a sense of those different structures, but it does kind of work.
All right.
Yeah. All right, so it's
So
10:25.
again, we've got a lot of that turquoise blue color,
Yep.
which tells us once again there's a lot of oxygen. There's more hydrogen than oxygen, but because of the ultraviolet radiation coming from the black hole at the center,
White
the
dwarf.
white dwarf at the center.
White
Thank
dwarf
you.
at the center. That's okay.
Yeah, I have an excuse. So anyway, the white dwarf at the center is pointing out ultraviolet radiation, which is ionizing oxygen and causing it to glow. Oxygen, when it's ionized like that, glows very, very bright, much brighter than the surrounding hydrogen, which is also there. All right.
Don't feel bad, Gerald. I remember I told everybody earlier that I was showing them pictures from next week.
Well, we're asking Gerald to do a bunch of things while he's talking at the same time.
That's right.
Yeah. And things are getting whispered in my ear and stuff. I'll never make it as a news announcer.
No, none of us.
Okay, so when you're ready to stop, I think we'll go to our surprise object.
Yeah, I'm ready to stop at any time. So
Yeah,
I'll just abort this.
We're good. It's just clearing the dome over there now, so we're good.
Okay. And put on frame and focus and go ahead.
All right, I'm going to go to Vega first to kind of make an intermediate stop.
Should go to Altair.
Vega's fine.
Make a couple of jumps. All right, sync on that, and then we'll go south to Altair and go there, do the same thing. And once again, do some
zeroing in.
Yep.
There we go.
Okay, time for our surprise item here.
Stephanie is ready for the surprise. She thinks she knows what it is, so we'll see.
Don't give it away.
I got to meet Stephanie last week, man. It was so cool.
Oh, sorry, I missed it last week.
It's Saturn. So Saturn has been slowly working its way farther and farther to the west, and it is now well above the horizon this time of the night. And low in the sky, so it's not real crystal clear, but we can see it. I'm all tweak with the focus a little bit.
Yeah, we could have some heat coming off of Rachel Stone there too.
Yeah,
it's going to distort this a bit, but
there we go.
It looks pretty good.
Yeah, we are looking right over the dome of the adjacent observatory. So there's probably some heat coming off the dome as well, which is making our image less attractive. But if you had any doubts about Saturn having rings, I think you can see that it definitely does. And over the next several weeks, as Saturn moves farther and farther to the west, we will be able to see it easier and easier, and we will not have to worry about the dome. And actually, as it moves west, it will also be moving higher in the sky, so we'll be looking through less atmosphere. So we ought to get even better views as we get later on in August. So something to look forward to. But tonight was the first time that it was clear of the dome next to us. So we thought, good time to introduce you to Saturn just before it's time to call it a night.
And it also means we kept a campaign promise.
Yeah.
Last week you said we were going to be able to look at Saturn this week, and we did.
We just barely made it too. It just became visible just a few minutes ago.
Yeah, that's why it's blurry so much, and it looks like it's swimming. You're seeing it underwater or something. Turbulence in the air, especially the turbulence right above the dome because of the hot surface of the dome. So it's not an ideal view, but like I say, over the next few weeks, it's going to get better and better. So something to look forward to. And then in a few weeks, the planet Jupiter will also be popping up. So,
hey, Bob asks a good question here. Can you explain the color fringing? I have a feeling that's because of the camera.
It may be because of the camera. It's an artifact. By all means, it's an artifact. Yeah.
It might also be because of refraction in the atmosphere, because it is kind of low in the sky. So it might be a combination of things.
It's interesting that it's blue on one side and yellow
that's why
reddish on the other side. Yeah,
that's why I think it's atmospheric refraction that's doing that. Yeah.
All right.
Okay.
Well, it
was great that we could end with that.
It's 10:30. I think we had a great night, and I hope you all enjoyed this. And we'll see you next week. And if there's no more questions, we'll bid you farewell.
All right. Good night, everybody.
Good night.
Good night.